Somewhere in a pair of colliding galaxies, 9 billion light years from Earth, there is a black hole 20 million times heavier than our Sun, and it is running away from home at 2.2 million miles per hour, fast enough to cross the entire distance from the Earth to the Moon in about 11 minutes, and fast enough to cross the width of the continental United States in under 5 seconds. It didn't drift off quietly. It was thrown, flung out of the center of its galaxy by one of the most violent events physics allows. And now it's plowing through raw intergalactic gas so hard that it's punching a glowing, star-forming tunnel 200,000 light years long behind it. A tunnel longer than our entire Milky Way galaxy is wide. For 50 years, physicists predicted that something like this should exist. A black hole so thoroughly evicted from its own galaxy that it becomes a rogue object drifting through the emptiness of intergalactic space alone forever. But predicting something on paper and actually catching it happening in the real universe are two very different things. In 2023, a team of astronomers led by Yale's Pieter van Dokkum stumbled onto a strange, thin, glowing line in a Hubble Space Telescope image, a line that shouldn't have been there. It took years of additional observation, and finally the James Webb Space Telescope, to confirm what they were actually looking at: the wreckage trail of a supermassive black hole that got kicked out of its galaxy and is now sprinting through the void, alone, forever. This is the real story behind the headline, "James Webb Caught a Giant Black Hole Lost in Space." And unlike a lot of what circulates under similar titles, this one doesn't need any exaggeration. The real science is already this wild. Let's get into it. Before we get to the discovery itself, we need to understand why a black hole leaving its galaxy is such an enormous deal in astrophysics. Every large galaxy in the universe, as far as astronomers can tell, has a supermassive black hole sitting at its exact center, an object that can weigh anywhere from a few 100,000 to many billions of times the mass of our Sun. Our own Milky Way has one called Sagittarius A Arc, weighing about 4 million solar masses. These central black holes aren't just passive residents, they're deeply anchored there by gravity, sitting at the bottom of the deepest gravitational well in the entire galaxy, surrounded by the dense concentration of stars, gas, and dark matter that built up around them over billions of years. Knocking one of these things loose isn't like nudging a marble. It's more like trying to physically remove the foundation of a skyscraper while the building is still standing. So how, in theory, could you ever eject something that massive from a position that stable? The answer lies in what happens when galaxies collide. Galaxy mergers are not rare, cosmic freak accidents. They are a completely normal, expected part of how large galaxies grow over cosmic time. Our own Milky Way merged with smaller galaxies multiple times in its past, and is on a slow collision course with the Andromeda Galaxy right now, a collision that will unfold over billions of years. When two galaxies merge, their central supermassive black holes eventually sink toward the center of the new Lie-combined galaxy, and over time can form a bound pair, a black hole binary, two black holes orbiting each other. Here's where it gets interesting. If a third galaxy merges in before that first binary pair actually collides and merges into one black hole, you can end up with three supermassive black holes interacting gravitationally at the same time in the same crowded galactic core. Three-body gravitational interactions are famously chaotic and unstable. In many configurations, physics resolves that instability by ejecting one of the three objects entirely, flinging it out of the system on a straight trajectory at extraordinary velocity, using the combined gravitational energy of the other two as a slingshot, while the remaining two settle into a tighter, more stable orbit around each other. This is sometimes called a gravitational slingshot, and it's the same basic principle spacecraft engineers use intentionally when they send a probe on a close flyby of a planet to gain speed, except here, the spacecraft is a black hole with the mass of 20 million suns, and the planets doing the slingshotting are two other supermassive black holes. It helps to picture the mechanics a little more concretely. In a three-body gravitational system, energy and momentum still have to be conserved overall, but they don't have to be shared equally between the three objects. What tends to happen, according to the physics of these interactions, is that the lightest or most loosely bound of the three black holes gets kicked out at high speed, carrying away a disproportionate share of the system's kinetic energy, while the two heavier or more tightly bound black holes lose orbital energy in the process and sink into a closer, faster orbit around each other as a result. It's a genuine trade. One object's violent expulsion is the direct mechanism that allows the other two to bind more tightly together. Nothing about this violates any conservation law. It's simply how chaotic three-body gravitational systems tend to resolve themselves, whether you're talking about three stars, three planets, or, in this extraordinary case, three black holes, each individually more massive than millions of suns. This mechanism was proposed theoretically decades ago as one possible outcome of the messy, chaotic process of galaxy mergers. But a prediction sitting in a physics paper is not the same as a confirmed detection. For 50 years, nobody had unambiguous observational proof that this had actually happened anywhere in the universe. That's what changed with this discovery. The story doesn't actually start with James Webb. It starts back in 2023, and it starts with a stroke of pure luck. Pieter van Dokkum, an astronomer at Yale University, and his colleagues were examining an archive Hubble Space Telescope image, studying an entirely unrelated foreground galaxy, when something caught their eye. A strange, almost perfectly straight, thin line of light that seemed to point directly back toward the core of a distant galaxy. Van Dokkum later described it as a bit of serendipity. They weren't looking for this at all. They had simply never seen a feature quite like it before, and its unusual razor-straight geometry was enough to make the team stop and take a much closer look. Curious and slightly baffled, the team followed up about a month later using the Keck Eye telescope in Hawaii, equipped with a spectrograph capable of analyzing the actual chemical composition and motion of light coming from an object, rather than just its brightness. What they found was that this narrow streak of light wasn't some imaging artifact or a chance alignment of unrelated background objects. It was real, physical, glowing gas and newly formed stars, stretched out in an almost perfectly straight line, roughly 200,000 light-years long. For scale, that's about twice the diameter of our entire Milky Way galaxy, compressed into what looks, from Earth, like a single thin thread of light. At one end of that thread sat a distant galaxy. The other end, at the very tip of the line, was a bright, compact knot of a very specific kind of emitted light called ionized oxygen emission, the kind of glow you'd expect from gas being violently shocked and heated. Van Dokkum's team proposed, based on the 2023 Hubble data alone, an extraordinary interpretation. They were looking at the visible wake of a supermassive black hole that had been ejected from that distant galaxy roughly 40 million years earlier, following a three-body interaction between three merging black holes. As the ejected black hole rocketed away from its home galaxy at enormous speed, it was plowing directly through the tenuous gas that fills the space around galaxies. That collision compresses and shocks the gas hard enough to trigger it to collapse and form brand new stars in a trailing wake. The same basic idea as the wake a speedboat leaves behind it on open water. Except here the boat is an invisible black hole and the water is intergalactic gas. It was a genuinely stunning proposal published in the Astrophysical journal Letters in 2023, and it made headlines around the world at the time. But Van Dokkum and his co-authors were careful, responsible scientists about it. The 2023 paper described this as strong circumstantial evidence, not an ironclad, direct detection. You can infer that a black hole caused a wake without ever having directly, unambiguously detected the actual physical signature of the black hole punching through gas at supersonic speed. To go from "this is almost certainly a runaway black hole" to "we have directly confirmed a runaway black hole," the team needed sharper, more sensitive data. They needed James Webb. This is the part of the story where the headline "James Webb caught it" becomes literally true rather than exaggerated. Van Dokkum's team went back to this object, now cataloged in their research as RBH1, short for Runaway Black Hole 1, with the James Webb Space Telescope, using its powerful infrared imaging and spectroscopy instruments to look for something very specific: a bow shock. A bow shock is exactly what it sounds like. The same kind of shockwave pattern you'd see piling up in front of a boat's bow as it cuts through water at speed, or in front of a supersonic jet cutting through air. If RBH1 really was a compact, extremely massive object physically ramming through intergalactic gas at a velocity faster than the local speed of sound in that gas, there should be a very specific, detectable pileup of compressed, shocked material directly in front of it, distinct from the trailing wake of star formation behind it. That is exactly what JWST found. The team's 2025 paper, titled JWST Confirmation of a Runaway Supermassive Black Hole via its Supersonic Bow Shock, reports that Webb's more sensitive, higher resolution infrared data revealed a clear supersonic bow shock at the leading edge of RBH1's trajectory. Direct physical evidence of an extremely massive, extremely compact object slamming through ambient gas fast enough to generate a shock wave, sitting right where theory predicted the actual black hole itself should currently be, at the tip of that 200,000 light-year trail first spotted back in 2023. In plain terms, the 2023 Hubble data showed the wake. The 2025 JWST data showed the wave breaking at the front of the boat. Together, that's about as close to catching a runaway supermassive black hole in the act as modern astronomy is currently capable of getting, without literally being able to photograph the black hole's event horizon itself from 9 billion light-years away, which is obviously far beyond what any existing instrument can directly resolve. Van Dokkum, describing the discovery afterward, put it about as plainly as a scientist can. It boggles the mind. The forces that are needed to dislodge such a massive black hole from its home are enormous, and yet it was predicted that such escapes should occur. The 2025 JWST paper, published as JWST Confirmation of a Runaway Supermassive Black Hole via its Supersonic Bow Shock, was co-authored by researchers spanning Yale, Harvard-Smithsonian Center for Astrophysics, the University of California, Santa Barbara, the University of Toronto, Tel Aviv University, and San Jose State University, a genuinely international multi-institution effort built on top of the original 2023 chance discovery. That's typical of how a lot of the biggest astronomical confirmations actually happen. Not a single lab working in isolation, but a chain of researchers across multiple universities and continents, each contributing a different observational technique, imaging, spectroscopy, and finally space-based infrared confirmation, to nail down a result rigorously enough to publish with confidence. Let's actually sit with the scale of this thing for a moment, because the raw numbers are almost hard to process. RBH1 is estimated to carry a mass of roughly 20 million times the mass of our Sun, smaller than the largest known supermassive black holes, which can reach billions of solar masses, but still an object so dense and massive that it would completely dominate the gravity of any ordinary galaxy it happened to sit at the center of. It's currently moving away from its former host galaxy at a measured speed of about 1,000 kilometers per second, which converts to roughly 2.2 million miles per hour. To put that in a comparison that actually means something, that's about 3,000 times the roughly 40 million years, which is longer than the time separating us from the extinction of the dinosaurs. Because there are two genuinely fascinating black hole stories from the Van Dokkum Research Group circulating right now, and it's easy for headlines to blur them together. It's worth being precise about a second, related but distinct discovery: the cosmic owl. In 2025, the same broader research collaboration studying unusual JWST images identified a separate, extraordinary galaxy system nicknamed the cosmic owl, officially cataloged using the symbol for infinity because of its shape, two overlapping rings of galaxy material that, together, resemble a giant owl's face staring out of the image, or an infinity symbol depending on the angle. The cosmic owl system contains not one, but three active supermassive black holes, with one of them sitting unusually not inside either of the two merging galactic nuclei, but out in the gas cloud directly between them, an anomaly researchers are still actively investigating. Initially, some researchers speculated this third, oddly placed black hole in the cosmic owl might itself be a runaway that had escaped from one of the two merging nuclei, similar in concept to RBH1, but follow-up analysis using JWST's integral field spectroscopy, a technique that captures a full spectrum of light across every point of an image simultaneously, rather than just at a single point, led the same research team to conclude the cosmic owl's third black hole more likely formed in place, directly out of the dense surrounding gas cloud through a process called direct collapse, rather than being ejected via a three-body slingshot. This is itself a hugely significant separate discovery. It may represent the first direct observational evidence of a supermassive black hole caught in the act of forming, which helps address one of the biggest open puzzles in astrophysics. How do black holes get so incredibly massive, so incredibly quickly in the early universe, sometimes appearing to already weigh millions or even billions of solar masses within the first billion years after the Big Bang? A black hole forming rapidly through direct collapse, rather than slowly growing over billions of years by gradually swallowing material, would be one compelling piece of that puzzle. So, to be precise, RBH1 is the confirmed runaway, ejected black hole detected via its wake and bow shock. The cosmic owl's third black hole is a different object entirely, in a different galaxy system, and current evidence favors it having formed in place rather than having escaped from anywhere. Both discoveries come from the same broader Yale-led research effort digging through JWST's Cosmos Webb survey data, which is likely why the two stories sometimes get merged together in less careful reporting. Beyond the sheer spectacle of a 20 million solar mass object rocketing through space at 3,000 times the speed of F-sound, this discovery answers a genuinely important open question in astrophysics and opens up several new ones. For decades, the three-body gravitational ejection mechanism for supermassive black holes existed only as a theoretical prediction, useful for modeling, but never observationally confirmed. Now that scientists know precisely what signature to search for, and what a linear wake of star formation, n capped by a supersonic bow shock, they have a genuine template for finding more examples hiding in existing and future survey data. As Van Dokkum put it, now that we know how to look for them, we can find other examples, and then we can answer the question directly from data by counting the number of escapes. Mergers between galaxies happen regularly over a galaxy's lifetime. Any galaxy roughly the size and mass of the Milky Way has likely experienced several mergers throughout its history, which means multiple black hole systems. And the conditions for these three-body slingshot events should form fairly often across the universe. What remains uncertain is exactly how quickly those black hole pairs actually merge, if they merge at all, and how frequently the resulting gravitational kick is strong enough to fully eject one of them from its host galaxy altogether, rather than just nudging it into a wider orbit within the same galaxy. That has real consequences for how astronomers understand galaxy evolution more broadly. Supermassive black holes are thought to play an active role in regulating star formation within their host galaxies, through processes like blasting out powerful jets and winds that can either trigger or suppress the birth of new stars depending on the circumstances. If a meaningful fraction of galaxies across cosmic history have, at some point, had their central black hole entirely removed via ejection events like this one, that could meaningfully change models of how those galaxies subsequently evolved, without the gravitational anchor and energetic influence a central black hole normally provides. It also raises a genuinely eerie possibility. There may be a population of galaxies out there right now quietly missing their central black hole entirely, having lost it to an ejection event sometime in the ancient past, coasting along largely unaware, so to speak, that the gravitational anchor that helped shape their formation is long gone, now drifting alone through intergalactic space, hundreds of thousands of light years away. There's another angle to this story worth unpacking, because it connects RBH1 to a completely different but related frontier of physics, gravitational wave astronomy. When two supermassive black holes spiral toward each other and eventually merge, in the final moments before collision, they radiate an enormous burst of energy in the form of gravitational waves, ripples in the fabric of space-time itself, first predicted by Einstein and first directly detected by ground-based observatories in 2015, though those ground-based detections have so far only caught much smaller stellar mass black hole mergers, not supermassive ones. Supermassive black hole mergers are expected to produce gravitational waves at frequencies far too low for existing ground-based detectors like LIGO to pick up. Instead, astronomers are hunting for evidence of these mergers using an entirely different technique, monitoring the extremely precise clock-like timing of distant pulsars scattered across the galaxy, watching for the tiny telltale timing disturbances that a background hum of gravitational waves from countless supermassive black hole mergers across the universe should, in theory, produce. RBH1 matters to this picture because a successful three-body ejection event, by definition, implies that the other two black holes involved didn't get ejected. They were left behind, now locked into a tighter, more strongly bound orbit around each other than they had before the interaction, which should make them merge together faster than they otherwise would have. Every runaway black hole astronomers find and confirm, therefore, is indirect evidence about the surviving binary system left behind in the original galaxy, and about how quickly the universe should be producing exactly the kind of supermassive black hole mergers that projects like pulsar timing arrays are trying to detect. In other words, catching a black hole in the act of leaving tells you something valuable about the black holes that stayed. It's worth pausing on a genuinely reasonable question. How does something this energetic, this massive, moving at 3,000 times the speed of sound, go completely unnoticed until a research team happened to spot a faint line in an old image almost by accident? The answer comes down to distance and brightness. RBH1 sits roughly 9 billion light-years from Earth. At that distance, even a 200,000 light-year-long trail of star formation appears, from our perspective, as an almost impossibly thin, faint streak of light, easily lost among the tens of thousands of other galaxies, stars, and structures crowded. Gee, any deep-field astronomical image. Black holes themselves emit no light at all. By definition, nothing escapes a black hole's gravity once it crosses the event horizon, which is precisely why they're called black holes in the first place. The only reason we can detect an object like RBH1 at all is indirect. We're not seeing the black hole itself. We're seeing the visible consequences of its motion, the wake of gas it disturbs, the stars that wake triggers into forming, and the shock wave that builds up ahead of it as it plows through the surrounding intergalactic medium. That indirect visibility only became detectable at all because of a combination of extraordinary circumstances. The ejection velocity happened to be high enough to generate a genuinely strong supersonic shock. The surrounding gas density happened to be high enough to produce a visible trail of new star formation rather than just a faint disturbance, and the trail happened to be oriented at an angle from Earth's vantage point that let it appear as a clean, resolvable line rather than being foreshortened into an unrecognizable blob. Any deep sky survey image contains thousands of galaxies and features, and a system like RBH1 depends on a human researcher noticing one unusual line among all of that clutter and deciding it's worth a second look, rather than simply moving on. That is exactly what happened here, and it's a reminder that even with our most advanced space telescopes, discovery in astronomy still frequently comes down to a trained eye recognizing that something in an image looks wrong, followed by the hard work of following that hunch all the way through to a confirmed detection. Did James Webb literally photograph the black hole itself? No, and no telescope currently could. Black holes emit no light. What JWST directly detected is the supersonic bow shock, the compressed glowing shock wave of gas piling up in front of the black hole as it plows through intergalactic space, plus the trailing wake of newly formed stars behind it. That combination is what confirms the black hole's presence in motion, even though the object itself remains invisible. How far away is this, and could it ever reach us? The system is located about 9 billion light years from Earth. Even setting aside the fact that it isn't moving toward us, an object that distant poses zero conceivable risk to our solar system. The light we're seeing left that galaxy roughly 9 billion years ago, long before Earth existed. Is this the same as the cosmic owl black hole story? No. They're related discoveries from the same broader JWST research effort, but they're different objects. RBH1 is a confirmed runaway black hole that fully escaped its host galaxy, the cosmic's Haitian. By detecting the actual supersonic shock wave the fleeing black hole is generating as it plows through intergalactic gas right now at 2.2 million miles per hour, roughly 230,000 light years from the galaxy it used to call home. It's the first confirmed example of a 50-year-old theoretical prediction finally catching up to reality, and now that astronomers know exactly what signature to search for, this almost certainly will not be the last one for her. And somewhere out there, right now, there may be dozens, hundreds, or more of these lonely rogue black holes drifting silently between galaxies, each one carrying the scar of some ancient, violent gravitational encounter, each one waiting for the next generation of space telescopes to notice the thin, glowing trail they left behind. There's something almost poetic about how this discovery unfolded. A black hole that fled its home 40 million years ago, in an act of cosmic violence involving 3 supermassive objects locked in a gravitational struggle, has been traveling alone through the dark ever since, announcing its presence only through the wreckage it leaves behind, stars born from the wound it tears through the gas in its path. It took a chance glance at an old image, a hunch worth following, and finally the sharpest infrared eye humanity has ever built, pointed at exactly the right patch of sky, for us to finally notice it was there at all. Multiply that by the billions of galaxies scattered across the observable universe, each with its own multi-billion-year history of collisions and mergers, and it starts to feel almost certain that RBH1 is not alone out there, just the first one we happen to catch.